Chapter 11 is going to focus on solutions, or in other words, homogeneous mixtures. In previous chapters, we learned about pure solids, pure liquids, and pure gases. Chapter 11 will look at some of the properties when we form solutions. Another name for a solution is a homogeneous mixture. A homogeneous mixture is alike everywhere and has a constant composition throughout. A solution is made up of two components, the solute and the solvent. The solute is the substance that is being dissolved. It's usually present in the lesser amount. So in our picture on the right, the orange spheres represent our solute particles that are being dissolved. The solvent is the medium that is doing the dissolving. Typically, our solvents will be a liquid. It's present in the larger amount, and usually our solvent will be water when we're dealing with aqueous solutions. Recall that the abbreviation for an aqueous solution is the subscript AQ. Attractive forces are very important in the formation of liquid solutions. The forces will hold solute and solvent particles together. It's important that we remember the intermolecular forces that we previously talked about. There are three types of interactions that can occur when we form a solution. There can be intermolecular forces between the solvent and solvent particles. There can be solute-solvent interactions, and also solute-solute interactions. The interplay between these three different types of interactions will determine if the solution will form or not. For a solution to form in the first place, the attractive forces between the solvent-solvent particles and the solute-solute particles must be about the same as the new attractions that will be set up between the solute and the solvent particles when we mix them together. We're going to look at three different molecules, water, benzene, and ethanol, and determine if solutions could form between pairs of them. Recall the types of intermolecular forces that are present in each of these molecules. The major intermolecular force in water is hydrogen bonding. We have two hydrogen-oxygen bonds present. In benzene, we have a network of carbon-carbon bonds and carbon-hydrogen bonds. Benzene is an overall nonpolar molecule, where the only major intermolecular forces that are present would be London dispersion forces, the weakest of the intermolecular forces. In ethanol, we also have an OH bond, which is one hydrogen bond present in our molecule, whereas water had two hydrogen bonds present per molecule. Nevertheless, both water and ethanol experience the same major type of intermolecular force. It's going to be important that we can analyze the structure and determine what type of IMFs are present before we can say if a solution will form or not. Let's imagine what would happen if we tried to make a solution by dissolving benzene in water. Benzene molecules are nonpolar overall. They are attracted to each other only by London dispersion forces, which are relatively weak intermolecular forces. Water, on the other hand, contains hydrogen bonding, which is a relatively strong intermolecular force. We also know that water molecules are polar. They have a partial positive charge that develops on the hydrogen and a partial negative charge that develops on the more electronegative oxygen. So the electrons contained within that covalent bond are being pulled more closely to the electronegative oxygen, which creates this polar molecule. Whereas benzene, being made up of only carbon and hydrogen, has a approximate electronegativity difference of 0 between the carbon-carbon bonds and the carbon-hydrogen bonds. Therefore, there are no partial polarities contained within this molecule, and the benzene ends up being nonpolar overall. The benzene molecules cannot hydrogen bond, and so they are not attracted to the water molecules very strongly at all. If a solution was to form to accommodate the benzene molecules, the water molecules would have to move apart to make room for them. This would require energy because the strong hydrogen bonds between the water molecules would have to be broken. The energy required to do this would not be balanced by the attraction of the incoming benzene molecules. Without the input of energy, the strong attractions between the water molecules will block the tendency for this solution to form. Therefore, we say that water and benzene are immiscible in one another, meaning they will not mix together in any proportions. The water molecules contain the strong hydrogen bonds, and the benzene molecules contain the weak London dispersion forces. Water is polar and benzene is nonpolar. Typically, we'll see a rule where likes dissolve likes, meaning polar molecules like other polar molecules, and nonpolar molecules like other nonpolar molecules. Since we have a combination of polar and nonpolar, forming a solution between these two is unfavorable. Now let's compare what would happen if we wanted to make a solution of ethanol in water. We said that water is a polar molecule and it contains hydrogen bonding, partial positive charges on the hydrogens, partial negative on the oxygen. Ethanol contains one hydrogen bond and it also has some carbon-hydrogen bonds as well. What's important is that there is this OH bond where we have a partial negative on the oxygen and a partial positive on the hydrogen. So overall the molecule will be polar because of that OH bond. So water contains hydrogen bonding as its strongest intermolecular force, and ethanol also contains hydrogen bonding as its strongest intermolecular force. The water molecules can attract alcohol molecules almost as strongly as they can attract each other. The forces that must be overcome when water molecules are pushed apart to make room for alcohol molecules is compensated by the similar attractions to the incoming alcohol molecules. Alcohol molecules moving into the water are surrounded by water molecules that attract them and will block them from moving out of the water again. Similarly, the water molecules moving into the alcohol will be caged by the alcohol molecules since they both contain hydrogen bonding. This means when water and ethanol are mixed, a solution will form. We say that they are miscible, meaning the two will mix together in any proportion. This is because they both can form hydrogen bonds with one another. The ethanol is soluble in water because when mixed, the ethanol-water attractions are not significantly weaker than the water-water attractions or the ethanol-ethanol attractions when the two were separate. Also, in terms of likes dissolve likes, both the water and the ethanol are polar. So since they're both polar, we would commonly assume that a solution would form between the two of them. To summarize, likes dissolve likes lets us quickly make an assumption about if a solution should form based upon the polarity of the molecules. When the solute and the solvent molecules are similar in polarity, the intermolecular forces that are set up between the solute and the solvent in the new solution will be about the same as the individual solute-solute particles and solvent-solvent particles. Therefore, they will tend to form a solution. Polar substances will dissolve well in other polar substances. For example, if we were making a salt solution or a solution of sodium chloride, we know that sodium chloride is an ionic compound made up of a sodium cation and a chloride anion. This ionic substance is very polar, and it will dissolve well in other polar solvents, such as water. Water we described as having hydrogen bonding, and it's a polar covalent molecule. Nonpolar substances will dissolve well in other nonpolar substances. Oil is a nonpolar substance made up of carbon and hydrogen bonds, and it would not dissolve well in water, but it would dissolve well in another organic solvent, such as something like cyclohexane. Cyclohexane is a six-membered ring composed entirely of carbon and hydrogen. Since it's made up entirely of carbon and hydrogen, it is overall a nonpolar compound, and the oil made up of all carbon and hydrogen will dissolve well in a solvent like this. So if we can analyze the polarity and the intermolecular forces of various molecules, we can determine usually if a solution should form. Likes dissolve likes also explains why oil and water don't mix together and form a solution. Oil, we can see, is nonpolar, made up entirely of carbon and hydrogen bonds. Its strongest intermolecular forces present will be London dispersion forces, whereas the water is going to be polar. it's going to form hydrogen bonds between different water molecules. So hydrogen bonding will be its strongest intermolecular force present. The hydrogen bonding is too strong of an intermolecular force to be broken by the weak London dispersion forces of the oil. So the oil layer will stay together and the water layer will stay together. We have nonpolar and we have polar, so we're not following that likes dissolves likes rule, and therefore no solution does not form. In a little bit, we are going to learn some definitions that will describe quantitatively how we can talk about how concentrated or how dilute a solution is. When we just say concentrated or dilute, we're simply talking about it relatively. Dilute solutions typically have a much smaller amount of solute present to the amount of solvent, whereas concentrated solutions have a large amount of solute particles dissolved in a small amount of solvent particles. If we look at the image on the left, we can see that the light red glass has less solute particles than the solvent particles. Therefore, we would call that solution dilute. There's a very small amount of solute actually present within that solvent, whereas the glass on the right appears a much darker red in color, and we would refer to that as being a concentrated solution because now we can see there is a ton of solute particles dissolved within the solvent. Three terms that are used to describe solutions are unsaturated, saturated, and supersaturated. An unsaturated solution is a solution where the maximum amount of solute has not yet been exceeded, meaning you could keep adding more solute particles and dissolve them in the solvent. It's unsaturated because you haven't exceeded that point yet. Whereas a saturated solution is the point where the maximum amount of solute has been added that can still remain dissolved in the solvent. This is a point where we've reached something called a dynamic equilibrium. In a perfect saturated solution, the amount of solute that's undissolved is going back and forth with the amount of solute that is dissolved. Recall that the double arrows mean equilibrium. And equilibrium means that the rate of the forward process equals the rate of the reverse process. So what this means is that the rate that the solute particles are becoming dissolved and then undissolving is happening at the same time. So it really looks like nothing is changing overall, but we've hit that perfect maximum amount of solute particles that our solvent can handle. We're at the capacity essentially. In a saturated solution, this means you're at that maximum capacity of solute particles that your solution can hold. If you were to add an additional solute particle to your solution, it would crash out as a solid instead of remaining dissolved in the solution. So that's where this equilibrium, this dynamic equilibrium comes into play, is that there's a change between the particles, the solute particles that are dissolved in the solution, and then them crashing out as a solid. We don't actually see this taking place since the rate forward equals the rate reverse as this process. But if we imagine in the middle here, this clump of sodium and chloride particles would represent solid sodium chloride. And here we have some dissolved ions, which are surrounded or solvated by our polar water particles. So these would be ions in solution. And the arrows are representing that the sodium ion could change and become part of the solid sodium chloride network, and a particle that's contained within our solid network could come out and become dissolved within the solution and be surrounded by water particles. So those arrows are showing the change between them, and the rate of this change is happening at the same time. Lastly, a supersaturated solution is a solution that has more solute dissolved in it than the solution will allow. Supersaturated solutions can only be prepared under special circumstances. If we make a solution of sodium acetate and we put it in some water and we warm it up, the increased temperature will allow the particles of sodium acetate to dissolve. We can add more sodium acetate than we could at room temperature. If we carefully allow it to cool down to room temperature and add one seed crystal of the sodium acetate, all of the sodium acetate contained within that solution will crash out and crystallize at once. Because supersaturated solutions are unstable due to them having excess solute dissolved within them than that solution would allow it to have under normal circumstances. So if we compare the three types of solutions, an unsaturated solution can accommodate more solute within it. Once we're at a saturated solution, no more solute can be added at a certain temperature and pressure, and there's that dynamic equilibrium between undissolved particles and dissolved particles within the solution. And a supersaturated solution is a special unstable type of solution where we've exceeded the solubility of that solution and crystals will crash out upon adding a seed crystal or if there's any kind of disturbance to that solution. As we go from left to right, from unsaturated, saturated to supersaturated, the concentration is increasing. There are many different units of concentration we can use to quantitatively describe how concentrated or dilute a solution is. Some of these are new and some of these we've seen before. Molarity is described with a capital M, and it means the moles of solute per liter of solution. Mole fraction is described with a capital X. This is a unitless quantity where we take the moles of some component over the total number of moles of the solution. So that component could be the solute or the solvent. If it's not stated, the component is usually the solute. Mass percent would be mass of the solute over the total mass of the solution times 100. Volume percent would be the volume of the solute over the total volume of the solution times 100. And then a new one that will be very important in this chapter sounds like molarity, but it's called molality. Molality is described using a lowercase m, and it's the moles of solute over the kilograms of solvent. You do not have to memorize any of these units of concentration. They will be given to you on any quiz or exam. You can print off a handout for this chapter that contains all of the equations within it on Blackboard and keep that next to you while we're practicing problems together. So we're going to do some examples where we practice calculating and interconverting between all of these various common units of concentration. Let's try an example. Given 45 grams of C6H6, which is benzene, the molecular weight is 78.11 grams per mole, and 80 grams of C7H8, which is toluene, molecular weight 92.14 grams per mole. Calculate the following: the mass percent, the mole fraction, and the molality. If we have a solution of benzene and toluene, we first want to determine what the solute is and what the solvent is. Notice that we have 45 grams of benzene and 80 grams of toluene. Since benzene is present in a lesser amount, this will be our solute. Since the toluene is present in a greater amount, this will be our solvent. Our mole fraction doesn't state if it wants it for benzene or toluene, so we're going to assume it's the mole fraction of the solute. First, let's calculate the mass percent. Mass percent will be calculated as the mass of the solute over the mass of the solution, so that's the solute and the solvent, times 100. The mass of our solute, which is our benzene, is 45 grams, divided by the mass of our solution. So we're going to have 45 grams from our benzene plus the 80 grams from our toluene. So we're going to have that whole thing in the denominator times 100 because it's expressed as a percentage. So for A, our mass percent of the solution should come out to being 36%. For B, we're going to calculate the mole fraction of the benzene. In order to do that, we're going to first have to do some unit conversions. We're going to have to convert both of our grams into moles. 45 grams of benzene. We can use the molar mass. We know it's 78.11 grams per mole. That gives us 0.576 moles for our C6H6 or our benzene. And starting with our 80 grams of toluene, we can use the molar mass or the molecular weight, same thing. We know it's 92.14 grams per 1 mole, and that gives us 0.868 moles of our toluene C7H8. To calculate the mole fraction of our solute, or X sub C6H6, that will equal the moles of C6H6, or benzene, over the total number of moles in our denominator. So we're going to have moles in our numerator and moles in our denominator, and therefore they will cancel one another, and this will be a unitless quantity. So our moles of benzene is 0.576 moles over our total moles of the whole solution. So that's going to be 0.576 moles for the benzene plus 0.868 moles for the toluene. Notice our units of mole will cancel, and our mole fraction of our solute will come out to being 0.399. A mole fraction, recall, will always be a decimal number somewhere in between 0 and 1. And lastly, C, our molality. Molality is our new term, and it's a lowercase m as the symbol. Molality will equal the moles of solute over the kilograms of solvent. So not of solution, but of only solvent. And we've already done the work of calculating the moles of solute, which is our benzene. So our moles of solute will be 0.576 moles over the kilograms of our solvent. Well, our solvent is toluene, we said, and we have 80 grams, so all we need to do is convert our 80 grams into kilograms and plug that into the denominator. So 80 grams in kilograms will be 0.080 kilograms. And notice our units are going to be moles per kilogram. So the molality of the solution will be 7.2 moles per kilogram. Another way that we can write this is by writing 7.2 with a lowercase m after it, and that stands for 7.2 molal. So both of those, whether you write moles per kilogram or lowercase m, are appropriate units for molality, and they mean the same thing. A bottle of sulfuric acid, H2SO4, is 25% by mass, and it has a density of 1.178 grams per milliliter. Calculate the mole fraction, molality, and molarity of this solution. Well, if we know we're dealing with sulfuric acid, the sulfuric acid must be the solute. Now, the problem doesn't mention what it's dissolved in, and in most cases, if it doesn't state specifically what something is dissolved in, that means that the solvent can pretty much assume to be water. If we know that the solute is present in 25%, we can assume that it's out of 100% total. the easiest thing to do is to cross off our percentages and assume that they are grams. So if we have out of 100 grams, 25 grams of it is our solute sulfuric acid, then 100 grams minus the 25 grams of solute will equal 75 grams of our solvent, which we just said is water. So we have 25 grams of sulfuric acid in 75 grams of H2O. First, let's calculate our mole fraction. In order to calculate our mole fraction of our H2SO4, we're going to have to do some unit conversions first. We're going to need the moles of our solute, which is our H2SO4, divided by our moles of water plus our moles of our solute sulfuric acid. Let's take our 25 grams of H2SO4 and convert that into moles. 1 mole of sulfuric acid can be calculated, and it has a molar mass of 98 grams, which gives us 0.255 moles of H2SO4. And starting with our 75 grams of H2O, we can convert that into moles. 1 mole of water has a molar mass of about 18 grams per mole, and that gives us 4.17 moles for our water. So taking those and plugging them into our calculation for the mole fraction of our solute, the moles of our sulfuric acid are going to go in the numerator, 0.255 moles for H2SO4, divided by the sum of the moles for the solute and the solvent, so 0.255 moles plus 4.17 moles for the water, and the units are going to cancel, so we have a unitless quantity for our mole fraction, and our mole fraction ends up coming out to 0.0576. Next, we'll calculate the molality, little m. Molality will be the moles of our solute, which is our sulfuric acid, divided by the kilograms of our solvent, not our solution. Our solvent is our water, H2O. So we already have everything we need. We already calculated the moles of our sulfuric acid, which we got 0.255 moles, divided by, well, our water we said we had 75 grams of, so we just need to convert our 75 grams of H2O into kilograms. So that'll end up being 0.075 kilograms for our solvent. Our molality when we divide ends up being 3.4 moles per kilogram, or 3.4 molal. Lastly, we're going to calculate the molarity. The molarity, or capital M, is moles of solute, so moles of H2SO4, divided by liter of solution. Well, we already know our numerator because we've used that several times, but we're going to have to do a little work to figure out our liters of solution. And in order to do that, we're going to have to utilize the density of the solution, because this density they give us is of the sulfuric acid in the water. So that's of our total solution. Recall that density is our link between mass and volume, and for our molarity calculation we need liters, so we need a volume. We knew that we started with 25 grams of our solute and 75 grams of our solvent, so we started with total of 100 grams of our solution. So if we start with that 100 grams of solution, we can use that density to get us into milliliters. The whole solution has a density of 1.178 grams per milliliter. Our units of grams will cancel. And then lastly, we need to convert that into liters. There's 1,000 milliliters in every 1 liter. And notice our units of milliliters will cancel. So the volume of our solution ends up coming out to 0.0849 liters. We can use that now in our molarity calculation. So coming back to our big M, our numerator is 0.255 moles for our sulfuric acid, divided by 0.0849 liters. So for this solution, our molarity ends up coming out to about 3 moles per liter, or 3 molar. It's important that you're careful with your lowercase m and your uppercase m's because they both mean two different things. And when also you're writing moles, not abbreviating moles for m. Let's try another example. Hydrogen peroxide solutions are sold at concentrations of 5% by mass with water as the only other ingredient. What is the molarity and molality of the solution? Assume a density of 1 gram per milliliter. So if we know that the solution is hydrogen peroxide and water, the hydrogen peroxide would be our solute and water would be our solvent. If we know that it's 5% by mass, that means that we can assume that 5 grams are our solute and 100 minus those 5 grams, or 95 grams, is equal to the amount of water. Next, we're going to want to take our 5 grams of hydrogen peroxide and convert that into moles using the molar mass. 1 mole of H2O2 equals 34 grams. And that gives us 0.147 moles of H2O2. To calculate the molarity, we're going to take the moles of solute divided by the liters of solution. So that'll be equal to our moles of hydrogen peroxide, 0.147 moles, divided by our total volume of our solution is equal to 100 grams. And since we're using a density of 1 gram per milliliter, 100 grams is also equivalent to 100 milliliters as well. Since the solution is pretty much water, this is a good assumption that we can make. So we're going to divide by the volume not in milliliters, but in liters. So 0.100 liters. And this gives us a molarity of 1.47 moles per liter. For the molality, we'll take the moles of solute and divide by the kilograms of solvent. So we're going to take the same numerator, 0.147 moles, and divide by our solvent in kilograms. Our solvent is water, and we have 95 grams, so we just need to convert that into kilograms. So 0.095 kilograms. And that ends up giving us 1.55 moles per kilogram.